Hello friends, so today I'll be talking about alkene stability and carbocations. So if you had to rank these four up here, how would you do so? Which one's the most stable and which one's the least stable? Well, the one that is the most substituted one is the most stable one. And why is that the case? Well, it's because of hyperconjugation. So if we were to look at something like this, we could say that this is more stable than this because this has more carbons. This is more stable than that because it has more carbons. So the one that has the least number of carbons, most hydrogens, is the least stable because of the hyperconjugation effect. So hyperconjugation effect is essentially what happens when you have single bonds as they're rotating around. Single bonds, they can rotate freely around their axis, so they can rotate 180 degrees. And as they do so, these p orbitals have the chance to overlap and share these electrons like so. So this electron can sometimes be shared. So that reduces that increases the stability of these carbocations. And whenever we discuss carbocations, the more stable one is the one that is more substituted or has more carbons. So for instance, this has 3 carbons, this has 2 carbons, this has 1 carbon, and this is just a methyl. So while we're looking at this is one rule we need to consider. How about another rule? We need to look at, how about double bonds and triple bonds? Well, single bonds are going to be more stable carbocations than double bonds. So if you have something like this, where you have a carbocation, like so. So you only have 3 bonds now because it's a carbocation, but the stability of this is lower because it has a double bond and it has less chance of rotating around its axis, allowing for the interactions between these p orbitals, which when they are aligned, they can interact. So the same applies for triple bonds. Triple bonds are less stable carbocations, but it's different for non-carbocations. So if you did not have this positive ion right here, positive formal charge, then we're talking about something else, in which case it would potentially be reversed. So you have to be careful. So we'll look at practice problems too after I discuss this final topic, which is on steric strain. So a cis isomer is less stable than a trans isomer. And that's sort of intuitive because if they're sort of bulky and they're next to each other, they're going to repulse each other because these carbons are positively charged and positive repels positive. So let's look at a few practice problems. Let's rank these carbocations by most stable to least stable. So one of the rules we discussed is looking for the substitution of the carbon due to the hyperconjugation effect. So if we were to look at this is a tertiary carbocation. This, however, is a primary carbocation because it only has 1 carbon connected to it. This is also a primary carbocation. This right here looks like it's a secondary carbocation, and this right here looks like it's also a secondary carbocation. But wait, if you look here, this is double bonded, so there's a potential for resonance. So if we think about it, resonance stabilizes structure. This is, if we draw the resonance structure of this, so this right here becomes, if you move the double bond here, because this is empty, you can only do this if it's empty. So if you have something like this, you can move this. You could push the pi electrons over so that now this becomes empty. But if you had something like this, you could not push. This is not possible simply because this has 3 hydrogens or however many hydrogens connected to it. And that would, you cannot break sigma bonds. You cannot have a pentavalent carbon or carbon connected to 5 things. So if we were to push the electrons, we get something like this. And this is a tertiary carbocation now with resonance. And this is without resonance. So if we had to rank these two between E and A, E is more stable than A. So now we covered E and A. Let's look at the secondaries. So there's only one secondary, so we know it's D. But between C and B, these are both primaries. So this is a primary with double bond. This is a primary without double bond. So this is more stable. So B is more stable than C. So we have the rankings where E is the most stable, and you can look at this and look at the reasoning. So we have 2 reasonings here. We have one that involves the hyperconjugation, but also considering the resonance. And the second one, the second rule is single bonds, double bonds, and triple bonds. So let's look at this as another example. So these are two separate problems right here. Is A or B more reactive when the carbocation is formed? And 2 is asking, is A or B more reactive when a carbocation is not formed, right? So when we look at a carbocation, right, the stability of the carbocation is determined by its how tertiary it is. So it looks like B will be the more stable answer. And the reason why this is the case, if you recall acids and bases in the previous video, we talked about how a stronger acid has a more stable conjugate base. So essentially, you want a stable carbocation so that it could be more reactive. Because if the carbocation is more stable, then it's more likely to be formed, which is more likely to be involved in the mechanism. And the reason why identifying what carbocation is more stable is essential is because later on when we discuss mechanisms, the major product that will be formed is generally the more stable carbocation, unless you have a specific mechanism that does an opposite effect. So looks like B is more uh, reactive carbocation. But what if a carbocation is not formed? So this happens when you have reactions where it just skips the carbocation step, like an SN2 reaction. So right here, the answer would be A, because of steric strain. So earlier we discussed steric strain, where right here this is a tertiary group, right? Tertiary groups have more steric strain than a primary group. So this is a primary group, this is a tertiary group, and this is a secondary group, and this is a secondary group. So between these two, the more carbons you have around something, the more steric strain there is, the more the carbons are trying to repel each other. So there are two forces here, they're fighting against each other. Hyperconjugation is fighting against the steric strain. So these are opposing forces. And because the carbocation is not formed, hyperconjugation effect is not very effective. So steric strain is the major force. So we want to go for the one that is less substituted, that has less carbons. So the primary one has only one carbon. The tertiary one has 3 carbons, so obviously we want to go with the one that's more reactive, that has less steric strain. So the reason for you would be steric strain for this one, and the reason here is hyperconjugation for you. So that's it for now. Then next time we meet, we'll talk about methyl shifts and hydryl shifts and alkyl shifts. So thank you for watching and hope you have a nice day.